Hi again, guys. So the power went back. I was cut off by the power outage here, but we're good now. Okay, so going back, um, yeah, right. We were here at -1. We subtract -1. That's why it's positive. So we're getting this portion in our second order determinant here, right? Now the thing is, how do we um, solve this thing? Well, the way we solved it was through diagonal, right? So we're going to multiply this and we're going to subtract it here, right? So how does that work? So that's 0 times 2 minus 1 times 4. And what do we get from there? Well, we have a -4. So this is 1 times -4. That's from here. And same idea, right? So we have -2. And here we have 3 times 2, 6. Minus -5 times 1. And so we have 6 plus 5. So we have 11. So 2 times 11. And then I'm going to put my head up a bit because I can't see. We have plus 1 times, so this is 3 times 4, 12. Subtracted to -5 times 0, so it's just 12. And we get our solution, which is -4 minus 22 plus 12, -38. So that's how we solve determinants, right? And the thing here is we can actually rewrite our definition for using second order determinants as the standard basis vectors, right? So if we now, oops, I don't know why it's lagging a bit. If we now rewrite, so we're going to rewrite definition 4. Definition 4 is this one. And we're going to rewrite it using second order determinants. Right? And the standard basis vectors we have I, we have J, we have K. We see cross product of vectors A and B. So we have A, which is A1I, A2J, A3 plus A3K, and we have our B vector, B1I, B2J, B3K. And we have this. The cross product of vectors A and B is this thing. A2, A3, B2, B3. I, Now, where did we get A2, A3, B2, B3? Where did we get that? Well, oh, from here, right? So what's happening here is we're multiplying A2 and B3. So A2 and B3 should be diagonals of each other. And we're subtracting that to A3, B2, which is here. Yeah, A3, B2. So that's the idea. And we're putting it in terms of I, J, K. Right? So now we're doing minus. Why are we doing minus? That's sus. Don't know why we're doing minus. Or did I do a minus here? Not sure. Okay, I'm gonna determine why it's a minus, but we're gonna continue. So this is A1, A3, B1, B3, right? This is J, because here now we're adding. Funny, right? We're adding A1, A2, A B1, B2. This is K, right? And similarly between equations 5 and 6, we often write this thing just for similarity purposes. So we have A x b. Let me know if I'm saying it wrong, because I think it's an x. This is I, this is j, this is k. And we have A1, A2, A3, B1, B2, B3, C1, C2, C. I'm kidding. I'm kidding. My bad. Oops. Yeah, it's only until here. Okay. Okay, so although the first row of the symbolic determinant in equation 7 consists of vectors, if we expand it as if it were an ordinary determinant, using the rule in equation 5, we obtain equation 6. The symbolic formula in equation 7 is probably the easiest way to remember and compute cross products. So we're going to use the 7th formula for cross products. So how do we do that? Let's go through an example. I'm also going to go through it. Okay, so example 1. So we're saying if A is 1, 3, 4, and B is 2, 7, -5, right? Then if we get their cross product, I'm just gonna call it the cross product. So we're going to be using I, J, K. And we're going to rewrite it this way. 1, 3, 4, 2, 7, -5. Now what? We can actually translate it to equation 6. So if we do that, we're getting 3, 4, 7, -5, I. Why is that? We're taking out I. That's like our headline, right? And we're getting this. Next, we're subtracting the J. So this is 1, 4, 2, -5, J. How did we do it again? I'm doing this. We're taking out that J column, and we're only looking at kind of the second and third row of I and k. Columns of I and k. We're looking at columns of I and k. And that's if we're plugging in the second order determinant. And similarly for k, it's just 1, 3, 2, 7. And then that's for k. All right, and now we can compute. So again, how do we solve second order determinants? We're getting their product diagonally, and we're subtracting them from each other. So what is this? This is negative 5 times 13, that's negative 15, minus 7 times 4, that's 28. Negative 5 minus 8 plus 7 minus 6. That's k, right? And then we now have a nice vector here, which is negative 43i plus 13. See how this is minus negative 13. So plus 13j plus k. 7 minus 6 is 1. This is actually just some vector. Negative 43. Oh, shoot. Negative 43, 13, 1. That's just a vector. So surprise, surprise. If we get the cross product, we get a vector. Whilst a dot product, we get scalar. We get a real number. Right? Dot product, we get some real number. Their cross product, we get some scalar. I'm kidding. Saying the wrong stuff. We get a vector if we get the cross product. We get scalar if we get the dot product. Right. Moving on. Example 2. Just encircle this. Example 2. So for this example, we're showing that the dot product, the cross product, we're showing that the cross product of the same vector A and itself is 0 for any vector A in V3. V3 means we have 3 components in that vector. So we have 1, we have 2, we have 3. 1, 2, 3. So we're doing it in 3D basically. Because that's how cross products work. They only work for 3D. Okay, so we just do this as normal. We use that formula. So we have I, we have J, we have K, A1, A2, A3, A1, A2, A3. And then what's next? We translate them, right? So for I, we have A2, A3, A2, A3. That's for I. Minus for J, A1, A3, A1, A3. That's for J. Plus for K, A1, A2, A1, A2. And that's for K. Then we simplify it even more. A2, A3 minus A2, A3. Funny enough, it's 0. That's I. A1, A3 minus A1, A3 J plus A1, A2 minus A1, A2 K. So yeah, I mean, it's all going to be a 0. This is 0I minus 0J plus 0K. 0, 0, 0. That's their vector. Simple enough, right? All right, moving on. We are going to look at the different properties of a cross product. So maybe here we'll find, oh, why do we use a cross product? Because remember, for dot products, we can use them to find angles. For cross products, I have yet to know. Okay, so we constructed the cross product of A and B, and it would be perpendicular to both A and B. So their cross product is a vector that's perpendicular to both A and B. And this is one of the most important properties of a cross product. So let's emphasize and verify it in the following theorem and give a formal proof. So here's the theorem. So we kind of talked about this the first time we encountered cross products. So we're saying the vector of the cross product of A and B is, we call this orthogonal, which is basically perpendicular to both A and B. So that's an important theorem, right? Now we're going to go through a proof. And I'm going to be honest, I like going through this. So let's go through it. Okay, now to show that the cross product of both non-zero vectors is orthogonal to, let's just do it for A. We're going to compute their dot products, right? Because remember, their cross product times one of their vectors is supposed to be 0. Now, how do we prove that? Well, let's just go through it normally. Okay. So, previously we did A2, A3. Actually, yeah, this makes sense. Yeah, let's go through this. B2, B3 of A1. Yeah, it's A1. Minus, we have A1, A3, and B1, B3 of A2. And then we have A1, A2, B1, B2. So we're using that formula that we did a while ago. It was 7, the seventh thing. Yeah, this idea here. So from 7, we're doing 6. Instead of IJK, uh-oh, probably messed up somewhere. A3. Oops, my bad. Anyway, yeah. So that's that's that. And then we simplify it. So we have A1 times, and now we solve the second order determinants. So it's going to be, probably should have done it here. Okay, I'm going to do it here. We go A1, A2, B3 minus A3, B2, right? We're just going diagonals here. We're subtracting those. Minus A2. We go A1, B3 minus A3, B1. We actually see a pattern here, funny enough. A3, A1, B2 minus A2, B1. Right? And then we can actually expand. So we have A1, A2, A1, A2. Right. A1, A2, B3 minus A1, A3, B2 minus A2, A1, B1. No, my handwriting is weird. This is supposed to be 3. B3, A2. Oh my goodness, what's wrong with my handwriting? A2, A1, B3 plus A2, A3, B1. So many stuff. Plus A3, A1, B2 minus A3, A2, B1. Now let's talk some similarities. I know I don't want to do this. Oh, look at that. I'm kidding. Let's see. A1, A2, B3, A1, A2, B3. Oh, look at that. These two cancel. Let's, okay, there we go. Oh, look at this. This and this cancel. A1, A2, B3. A1, A3, B2. Oh, look at that. These cancel. A2, A3, B1, A2, A3, B1. Oh, wow. So basically, everything is equal to 0. And so their dot product is 0. And if their dot product is 0, then they're perpendicular. So that's how we show uh, that they're orthogonal. And this also works if it's for B. We're just going to change A1, A2, A3 to be B1, B2, B3. And we're going to get the same thing. So that's the proof. Very long. Okay. So if A and B are represented by directed line segments, now what do we say by directed line segments? We say that they are vectors with the same initial point as in figure 1. I'm going to show you what figure 1 is. I'm going to take a screenshot. Okay. So let's move here. Here we're saying if A and B are represented by this thing we call directed line segments. Now, what about directed line segments with the same initial point? So here it's saying that these vectors have the same tail, right? Then theorem 8 says that their cross product A, B, points in a direction perpendicular to the plane through A and B, right? How does that look like? Well, I'm gonna put the screenshot of the picture. So here's a screenshot. I can't zoom it in. Okay. So what is this saying? Well, we have this vector A, this vector B. They have the same initial point there. They make an angle of theta. And here it says their cross product AB points in a direction perpendicular to the plane through A and B. So here you can see these are right angles. They're perpendicular to A and they're most certainly perpendicular to B. That's what that means. Okay, so it turns out that the direction of AB is given by the right hand rule. So yeah, we have a hand here. The right hand rule states that if the fingers of your right hand curl in the direction of a rotation through an angle less than 180 from A to B, then your thumb points in the direction of A to B. Now, I don't understand this personally, but what I do understand is that the the vector that this A the vector that this cross product of A and B points to is perpendicular to A and B. That's all I understand. So I'm not gonna focus about that right hand rule, but you guys can explain it to me what it means. Okay, now that we know the direction of this vector A, I'm just gonna say A times B. This A times B, the remaining thing we need to complete its geometric description is its length. So we need to find the length of this thing. So that represents with two vertical lines. Now, how do we get that? Well, we have another theorem to law that. All right, so we have this theorem here. Actually, I'm going to zoom this in a bit because it's cool. It's important. Okay, we're gonna go straight into another theorem. All right, so another theorem, it says that if theta is the angle between A and B, A and, oops, my bad, between A and B, and we're assuming this angle is in between 0 and pi, and the length, the length of the cross product A times B is given by, now we go straight into the theorem. So we have the length is equal to, oh, would you look at that? We talked about this. Oh, I'm kidding. It's not cosine, it's sine. My bad. Okay, right. Let's go through another proof. There's so many proofs. Wow. All right, let's go through this proof. Okay, interesting. I'm looking. Let's see how long. Oh, wow. So many proofs. Okay, I'm gonna go through this one, and then I will see you guys in the next video after I go through this proof, because it's a long proof. And I know you guys don't like watching long videos, so I'm just gonna go through this, and then we'll continue in our next video. All right, so what's the proof? Um, so from the definitions we had above of the cross product and the length of a vector, actually, twice that length of the cross product is A2B3 minus A3B2 squared. So here we're doing cross product, right? A3B1 minus A1B3. We're squaring that as well. Plus. I really should. I don't know if I should make my handwriting smaller or. Then we have A1, B2. Tell me, how many times have we seen the same thing? A2, B1. All right. And then here we can actually expand So, well, let's do that. I don't like doing this, but we're doing it anyway. So we have a2 squared b 3 squared. We're subtracting it to 2a 2a3 b2 b3. We're just expanding here. Plus a3 squared a no b2 squared. Right? So that's the first thing. Okay, now we're adding. So same idea. A3 squared b1 squared minus 2a3 a1 a3 uh b1 b3. Yeah, so there's like a pattern here. A2 a3 b2 b3 a1 a3 b1 b3, and then plus a1 squared b3 squared plus last one for this one. So we have a1 squared b2 squared minus 2 a1 a2 a1 a2 b1 b2, could be the other way around, doesn't matter, plus a2 squared b1 squared. All right. And from there, we're just going to do some more crazy looking algebra. I'm kidding. This is going to be simplified. So it's going to be a1 squared plus a2 squared plus a3 squared. So here we're just factoring out everything. We have b1 squared, b2 squared, b3 squared. Right? And then we have minus a1 b1 plus a2 b2 plus a3 b3, and that's squared. So we just cleaned it up a bit. And if you notice, these are actually the lengths squared. A1, A squared, the magnitude squared. These are magnitude squares, right? A1, A2, A3, they're squared. B1, B2, B3, they're squared. And we're subtracting it to, and voila, the dot product of A and B squared. A1, B1 plus A2, B2, etc. And here, if you remember from our old formula, A times B, or I keep saying it, the dot product, if we want to include that angle, we actually have a formula for that, which is, well, it's A1, A length of A squared, length of B squared. I'm putting in the squared, and then cosine squared, right? I put in the squared already, but it's the length of A times the length of B times cosine theta. So that's that formula for dot product if we want to get their angle. And then we just factor this one out, basically. So we have this factored out, and then we have 1 minus cosine squared. And 1 minus cosine squared, which is a trig identity, is sine theta. Sine squared theta. Sine squared. Sine squared. And would you look at that? We're now taking the square roots and observing that the square root of sine squared is actually just sine. Because sine theta is greater than 0 when our theta, remember we had the condition that our theta is in between or equal to 0 to pi. So basically, we're saying that sine theta is greater than or equal to 0, so it's positive, when 0 is less than or equal to theta less than or equal to pi, which we actually stated the same condition a while ago. There we go. An angle between A and B is an angle between 0 to pi. It can't go beyond that. And knowing since this is positive, then we get rid of the negative root. So it's just going to be a positive. So if we take the square root of sine squared, it's just going to be a positive. Right? So basically we have their cross product, which is A, B, sine. Right. Okay, that's it for now, and I'll see you guys in the next video.